Okay, so more alkene reactions. And tomorrow there'll be more alkene reactions as well. And after break, pretty much up till the last couple days. And then it'll be alkyne reactions, which are pretty much alkene reactions with two multiple bonds instead of just one. Okay, questions? Did you have any questions about today? What did I add in? Regio and stereoselectivity. Sure, do you have a particular molecule you want to?
Not really, I was confused when I did
The online quiz? Okay. So let's just say for the sake of argument that we have, I don't know, let's do this one. And what do you want to add to that? Let's add BR2 to it. So I'm always going to ask you what are the major products, and then I'll ask you, is the reaction regio, stereo, both, or neither? So in order to do this in order to determine that, you have to determine the products of the reaction. Okay, and again, this goes back to where we ended on Friday. What am I adding? How am I adding it? And how am I adding it? What am I adding? Markovnikov or now anti-Markovnikov? Cis, trans, 50-50. So if I was to write this, if I was to write the product or products of this reaction, what would they be? What am I going to add to a double bond? What does Br2 add?
Was it bromine at both points?
2 Brs. So I'm going to add 2 bromine atoms. So if I'm writing out my possible structure, I'm going to have a methyl group. I'm adding a Br to that carbon, and I'm adding a Br to that carbon. Did I add it Markovnikov or anti-Markovnikov?
Both. You have one on both A and B, carbon A and B.
And so I would say there is no Markovnikov, anti-Markovnikov. There's no Markovnikov or anti-Markovnikov addition because the bromines are symmetric. I'm adding the same group. So whether I add it this way or this way, it doesn't matter. I end up with the same product. Now you might say, but Markovnikov's rule says, where do you add the H? And there is no H here. Right? Anybody want to make that point? But if we broaden Markovnikov's rule out, what we're really talking about is where do I add the H plus? And in this case, the question is where do I add the Br plus? So Markovnikov's rule can be broadened out to not just say the carbon with the most hydrogens gets the hydrogen. I would go and say the carbon with the most hydrogens gets the electrophile, except in this case. Because in this case, what happens? Which carbon in the double bond does the Br plus add to? Top carbon? Anybody want to add another answer? The Br. So if I'm going to add my Br plus to this, where's the Br plus going to go? Carbon A or carbon B? cards up in my office. How many people say A? How many say B? How many say both? Why is it both? What does the BR do? Forms the triangular intermediate, right? Forms the bromonium ion. It's big enough to fit over both carbons, and when it does that, it then leaves each carbon with a delta plus charge. Why is it going to do that? Because then no one carbon has to take the positive charge. It can share, or it can delocalize. So for bromine, we're going to end up actually bonding to both carbons. So that's the bromonium ion. I had the right video up, right? Okay, because you're looking at this like, I've never seen this before. Ever. So the idea here is that I'm adding two BRs. In the end, there is no Markovnikov, there is no anti-Markovnikov. If the reagent is symmetrical, you don't take that into account. However, my third criteria, how does it add? Do these two bromines add 100% cis, 100% trans, or both? 50-50. What do we think? How many people think 100% cis, 100% trans? Both, 50-50. Well, a common rule now is whenever we have a triangular intermediate, that's going to block the Br minus from adding on the same side of the bromine, so it's going to have to add so that the BRs now are trans to each other. So it's 100% trans. Okay. If we didn't have that triangle, it'd be 50-50. But anytime we get a triangular intermediate, it's going to be 100% trans.
In the video, did you say we had to draw both forms, or that both forms?
Well, I'm coming up to that, okay? This is the product. This is 100% of that product. That's what we get, is 100% trans, addition of the bromine. All right, everybody still kind of with me? I don't think so, but I'll ask the question anyway. Break starts after tomorrow. So give me, all you need to do is just give me 100 minutes. 50 today, 50 tomorrow. And then you can have the rest of the week to yourselves. Maybe. So the question now becomes, if everybody's with me and I don't hear any questions, so the BR always adds 100% trans. So the question now is, okay, that is my major product of the reaction. Is the reaction regioselective, stereoselective, both, or neither? What does it mean to be regioselective? What are the characteristics of being regioselective? When am I going to think a reaction's regioselective?
That one different catchment of the atoms.
The regio part means that two structural isomers are possible, which is the different connection of the atoms. So that means for that reaction, you have two possible structural isomers. What does selective mean?
Yeah, major.
In other words, you choose one, right? That's what being selective is. So not, you have to have both of these criteria to be a regioselective reaction. You have to have two structural isomers possible as the product, and you have to choose one as the major product. If you get 50-50, it's not selective. Everybody okay with that? Except we have to apply it. Now let's do the stereo. Let me come over here and say, what does it mean to be stereoselective then? Well, we've already done the selective part, right? Got to have a major product, got to choose one over the other. How about stereo? What is going to be the relationship between my two possible products?
Isn't it how it binds like cis or trans?
Yeah, it sort of means that. But what about my two possible products? In regioselective, my two possible products were structural isomers. What are they going to be in stereoselectivity? They're going to be stereoisomers. My stereoisomers are going to be possible products. Well, I forget, and I bet I'm not the only one. What possible stereoisomers could they be? What are some possible stereoisomers that we've talked about this semester?
Enantiomers and diastereomers.
Enantiomers, diastereomers, cis-trans. Those are possible those are stereoisomers. So that means our products are maybe they're diastereomers, maybe they're enantiomers. Now, what would two molecules have to have in order to be either enantiomers or diastereomers? They got to have chiral centers. Just one for enantiomer, but two for diastereomers. So that's going to be important to look at in the product. Do we make a product with chiral centers? One chiral center, two chiral centers, so that we can tell whether we've made products that are diastereomers or enantiomers. Now in this product, in this reaction, my one product that I could make, and it's the 100% product, was that the bromines are trans. But what's the other possible product? And all I mean is the other possible product. Right? I've already basically said if I add the bromines this way and this way, I get the same product. Do I get the same product if I add the two bromines now cis? So is that a possible product? Sure. I could add the bromine cis or trans. Do I get two different products if I do that? Just like for regioselectivity, I'm going to say, well, if I add the two groups this way and this way, if they're different, and I selected one, guess what? It's regioselective. If I add the two groups cis and trans and I don't get 50-50, it's going to be stereoselective. If the two molecules are and enantiomers are diastereomers. So in this case, what's the relationship between these two molecules? They are what?
Diastereomers.
Diastereomers? We agreed? Okay, so I agree with that. These are diastereomers. Did I select one over the other? Yes, and here's why I say, that you choose one or you select, as opposed to necessarily major or minor. Your selection can be anywhere, your selectivity can be anywhere from, 50.5 to 49.5 to 70, 30, 80, 20, 90, 10, 100, 0. Unfortunately, we don't have a term that deals with 100% of a reaction product. So we say the reaction is stereoselective even if it produces only one product. Okay, so it doesn't have to be a mixture. If you get one product that's 100, 0, that's still selective. So this reaction would be stereoselective because the two possible products that I could make, the cis and the trans, are diastereomers, and I'm selecting the trans as far as the bromines go. Is it regioselective? Regioselectivity comes about with Markovnikov, anti-Markovnikov. So in this case, since I have a symmetrical reagent, I can't get to possible structural isomer products. I can't get that. And so therefore, there's nothing to select from. I'm only forming one structural isomer. But I am forming two stereoisomers, and I am selecting, so that's what makes it stereoselective versus regioselective. Does that kind of make sense? Let's see, I put a whole bunch of okay, there's three reactions. What I'm going to ask you to do, well, a week from this coming Friday, is I'm going to ask you to write the products and tell me whether the reaction is regio or stereoselective, both or neither. So the first thing is, can we write the major product of the reaction? Realizing that the minor product, or the product that we don't get 100% of, is important in determining whether the reaction is selective or not. But what are the major products of each one of these reactions, product or products? Can you do that? Then can you tell me, is it regio, stereo, both, or neither? If I'm doing this problem, I look at the first one. What am I adding? What am I adding to double bond? And I'm adding HBr. Okay, so I'm going to add HBr. Where's the H going? Carbon A, carbon B. A? We all in agreement? No? We want to add to B? We all in agreement that it goes to B? And then where's the BR go? Is there another possible product? I don't know. Let's see. Let's add the H to A, then the bromine to B. There is. Okay, so what's the major product, A or B? Or is it 50-50? How many people say A is the major product? B, 50-50. Okay, so the majority says A is the major product. Is the reaction regioselective then? Yes? Because what happened? I have two possible products. What's their relationship? They're structural isomers. They have different names, right? First one is 1-bromo 1-methyl cyclohexane. The second one is 1-bromo 2-methyl cyclohexane. So they're different structural isomers. Did I select one over the other in forming a major product? I did, because this reaction goes by Markovnikov's rule. So A is the major product. Therefore, this reaction is regioselective. What's my next question? Is it stereoselective? No. Now I actually know I could rule that out right now and say, nope, not going to be stereoselective. As a matter of fact, every single one of these reactions is not going to be stereoselective. But that's because I know that. But you should know that too. Right? Sometimes it's easier to write rules of when this happens, it will never be. Right? If we add symmetrical reagents, or we have a symmetrical alkene, the reaction will never be regioselective. Right? Because if one of the two things is symmetrical, it doesn't matter which way I add, I end up with the same product. So that's a rule we can learn or remember. Symmetrical, I look at these, they're not symmetrical. So every one of these could be regioselective. But then I look at them and I go, nah, they're not going to be stereoselective because I know the other rule. And the other rule is a reaction will never be stereoselective if. Nobody want to finish that? The reaction will never be stereoselective if. It has. True. It'll never be stereoselective if you only make one product. But I have an even better rule. Well, that's when it could be. Non-symmetrical reagents could be regioselective, but I'm not talking stereoselectivity. So a reaction's never, when is it never going to be stereoselective? Think about the possibilities. Give me a characteristic of a reaction that could be stereoselective. How about the last one? Which was like way back here. That was stereoselective. Give me a characteristic about that made it stereoselective.
There was a cis-trans options, and there were stereoisomers.
In other words, this reagent had the ability to do what? Add 100% trans. So if you have a reaction that adds 100% cis or trans, it could be stereoselective. Could be. But all the reactions that I wrote down here, they're still not regioselective. So you could say, okay, they're not regioselective. That must mean that adding HBr and peroxide, H plus H2O, those must not add 100% cis or trans. As a matter of fact, they don't. What do they add? 50-50. Every time? Every time. They always add 50-50. Why?
Because they go through a carbocation.
They either go through a carbocation or, down here, what's our intermediate? Come on, I hear it. No. Not that one, not with HBr and H2O2. But I'll go back, your triangular intermediate, every time you have a triangular intermediate, could be stereoselective. Right now, probably will be. Maybe. What's that one go through? It's not going to be stereoselective if you go through what kind of intermediate? I hear carbocation. I agree with that. But there's one more. Carbocation or. What does this one do? Oh, look at that. I have a little eraser that I never had before. HBr H2O2, what kind of intermediates does it go through? I'll give you a hint. There's an initiation and a propagation step to HBr H2O2. Right? That was in the, was that not in the video? Where's initiation and propagation? What does that refer to? Radical. If you go through a radical or a carbocation intermediate, you lose the possibility of being stereoselective. As a matter of fact, I would broaden that out and I would say if you have an sp2 intermediate, there's no stereoselectivity. Why? Because what you're going to end up with is you're going to end up with a sp2 hybridized intermediate Maybe in the carbocation case, this is empty, there's one electron there. Either way, the nucleophile that adds after that is 50-50. And so you're going to end up racemizing that center. So you're going to end up with 50% cis and 50% trans. And when that happens, there is no possibility of being stereoselective. So there's our big rules to remember. I mean, you can eliminate half my problems that way. If it's symmetrical, it can't be regio. If either one is symmetrical. If you go through a carbocation or a radical, can't be stereoselective. So I look at all three of these and I go, nope, no stereoselectivity there. Is there regioselectivity? Maybe. Or is everybody still kind of with me?
So that last one was stereoselective because of the bromonium ion.
Yes.
Okay. So
Because-
they never went through a carbocation or.
Exactly. One of the things we're going to find is that when we form the triangular intermediate, those will always have the ability to possibly be stereoselective. Most times they will, but you have to take these on a case-by-case basis. But if you have a triangular intermediate, that's a pretty good possibility. Let's take the last one. What am I adding? Last reaction. What am I adding to the double bond? I'm going to have to put the class roll on my iPad because I have this cute little program called the Stick Picker. And I just push the button and it gives me a stick with somebody's name on it so that I can call on them randomly so I'm not picking on them. But I haven't loaded up the roll yet. I might have to do that for tomorrow and for next week and for next semester. It'll keep everybody awake. What was my question? What are we adding? What are we adding? We're adding an HBr. An H and a BR. All right? So I've got a methyl group there, a methyl group there. And so how am I going to add my two? What am I adding? I'll add the H there, the BR there, the BR there, and the H there. Notice I didn't have to know anything about the reaction to do that. Right? I didn't have to know mechanism. I didn't have to know Markovnikov. All I needed to know was I'm adding H and BR. And the double bond disappears. So there we go. There's my two possible products. We'll call them A and we'll call them B. In this reaction, what's the major product? How many people say A is the major product? B? 50-50? Okay, HBr and hydrogen peroxide, Markovnikov or anti-Markovnikov? It's anti-Markovnikov, which means that the H now goes on the carbon with the least hydrogens. It's the exact opposite. So A is my major product for this. A is my major product. Regioselective? Yes? Regioselective? Stereoselective? No? We sure? Should be. Because that's what this says. Is it regioselective? Yeah, didn't I say a few minutes ago that all of them were regioselective? Well, I probably said they all could be regioselective. We okay with that? Regioselective only. Middle one. All right, middle one. What am I adding to the double bond? You guys are too much.
H plus
And
OH.
H and OH. Okay. Great. Let me add the H and the OH to two possible ways, which I just did. So there's my two possible products. Again, did I need to know anything about the mechanism to do that? No. What did I need to know? Just erase the double, write the molecule out with that double bond, put one group here, one group there, one group there, flip them. That'll get you some points. Right, it won't get you all the points, but it'll get you some. Which product is the major product? A. How many people say A is the major product? B. 50-50. 50-50. H plus H2O goes by what rule? Markovnikov's. What am I adding? H and OH. Markovnikov. 50-50 cis and trans. Now, for this molecule, when I add my H and my OH to form the two possible products, there's no Markovnikov product, right? Because the H will add to the carbon with the most hydrogens. In this case, the two carbons in the double bond have the same number of hydrogens, 0. And so therefore, I'm going to add to both carbons equally. And so in this case, this one is not regio. This one is regioselective. And all of these are not stereoselective. So here's what we need to do as we learn more reactions, which we'll go through a few tomorrow. I guess I'll record the video, although remember, break doesn't start until at the end of the day tomorrow, although you may start yours a little earlier. I will not start mine earlier. If you have other professors who do, they're violating the rules. But nobody cares. Every time we have a new reaction, think about it this way. What am I adding? What two groups am I adding? Because you can just write the products, right? You can just write the possible products. And there's only two possible products. You're either adding this way or this way. So we need to know, what are we adding? Does that reaction go by Markovnikov or anti-Markovnikov? Does that reaction add 100% cis, 100% trans, or 50-50? And if you know those three things for each and every reaction that we're going to talk about, you'll at least be able to write the products. And you'll be able to identify the major product. And you'll probably be able to take at least a guess as to whether it's regio or stereoselective. But remember, those big rules that I just kind of laid out will eliminate a good portion of the possible reactions. So now what we have to do is now we have to think about a few more reactions. So we had HBr, H2O2 for today, Br2. Now we've got to think about adding Br2 and water. Right, was that in the video for today? The Br2 and water? What's Br2 and water add? So everybody scrambles for their notes to see if they wrote anything down. Well, if it's not there, then I guess that's where we start tomorrow. So we'll talk about Br2 and water. We'll talk about H2. How do we add H2? And then how do we add H and OH differently? Like, how do we add HOH anti-Markovnikov? How do we add H and OH so it's 100% trans? Joe?
Mercuration and demercuration. Are related to that.
Right, we're gonna talk about that. That's what that's, the mercuration, demercuration is a way to add H and OH. Markovnikov and 100% trans. So we'll talk about those mechanisms. So I'm a lecture tomorrow. Like I said, I'll try and record it. So if you come in and you're not on top of your game, you can watch it later. Of course, it'd be better just to watch it once, live. No in-class quiz tomorrow. That's why we had the in-class quiz today. Hopefully that didn't just, keep you from coming tomorrow. But that's what we'll do. I hope to have all of these quizzes and stuff graded outside my box at the end, and I'll have the updated scores online along with all the answer keys posted. So that's my goal today. All right.